Hello. Hi, today we'll talk about B-tree index in Oracle, exactly how it does it work, how Oracle implements this B-tree index, and how does it helps in making query faster. So before understanding that, let's look at this start from the basics, like how Oracle look for data and gets the data from the disk. Have a table, employee table, with all the columns listed here and data types, and each column has maximum it takes up some bytes. So if you add up everything, it comes around 206 bytes. Just assume 200 bytes approximately for easy calculation. So number of rows per db block is 8 kb. Standard block size is 8 kb. Let's say 8,000 bytes and 200 bytes per row. So you can have at max 40 rows in one block. I know there are some space is taken up by PCT free and block header and everything, but just for easy calculation, just say that at max it can hold 40 rows in one block of this employee table. Now, if you have 100k rows of this table, now this index works effectively when you have more number of rows, like 100,000 or close to millions or more than a million rows. So for 100k rows, how many blocks you need? You need 100k by divided 40 is 2500 blocks. So if your Oracle is doing a full table scan, you say is looking for employee ID 1001 and doesn't have an index on employee ID, so it has to do a full table scan. So it has to read 2500 blocks. Now for a full table scan, Oracle does a multi-block read. It reads multiple blocks at a time. There's a parameter called, I think, db multi-block read count, and it's set to by default like 128. It's a platform dependent, but the thing is, it can read multiple blocks in one IO, disk IO. And also it can do a direct read path in case of full table scan. So it bypasses the DB buffer cache, directly transfer that to PGA. But it does a lot of things. Oracle does a lot of things to make full table scan faster. But nonetheless, it has to read 2500 blocks in this case. Now, how can we make it faster by implementing a solution in the direction of index? Let's take a look. Let's say we create one more table which will have only employee ID in each row, one employee ID from the main. This is the main table. So I'm creating one more kind of a lookup table which has only employee ID and a pointer to the row. This pointer in Oracle is it's called row ID. Row ID is the fastest way to access any row in Oracle database. So it is 18 character long. It looks like this, and character 1 to 6 is data object number, 7 to 9 is data file number, 10 to 14 is database block number, and 15 to 18 is row slot number. So if you give a row ID to Oracle, it can directly go to the file and the block number and find the row slot number, and find the row very, very quickly. So every row in this lookup table has a row ID, and it can go once do it. But anyway, the Oracle has to read the entire lookup table. So how many block that is? So this employee ID is 10 byte, and this row ID is the record pointer. Row ID is 18 bytes, so it's 28 bytes. Let's, for easy calculation, let's say 25 bytes. So in a single block, it can have 320 rows of this lookup table. Now, how many blocks you need to read the entire lookup table? That is 100k divided by 320, 313 blocks. So for main table, 100k rows is 2500 blocks, and for the lookup table, the 100k rows is 313 blocks. So if I ask you to find the detail for employee 101, so you read this 313 block from here, find the 101, get the row ID, and then go to that row and read that block. So it will be 313 plus one block to read the actual data, 314 blocks. But it's still very, very high. It's imagine what you have like a million rows. It's still, this lookup table is not that efficient. So let's go further and create one more lookup table on top of that first lookup table. And so in the first lookup table, you need 313 rows, and each block can contain each block can contain 320 rows. In the first lookup table, you see this red box, that is one block that contains 320 rows. What if we create another lookup table which has a range of this 320 and then point to one block? So 101 to 421 is 320 rows. It point to the first block, and 422 to 742 is another next range, and you point to the next block like that. So how many blocks you need in the second lookup table? Because the first lookup table has 313 rows, and the second lookup table points to one block, one row points to one block, so it will have 313 rows. That I can keep it in a single block, one block, because it will be the same size like one block, 313 rows, because this has 313 blocks, so you'll have 313 rows. So that I can store in one block, because in one block I can store 320 rows. So now, to find a record how many blocks I need to read, I need to first read this second lookup table, one block, find the block pointer, record pointer, and then read that block from the first lookup table, which is another block. So one block plus one block, two blocks. Find the row ID, then go to the actual table and get the actual row. That is one more block. So I need three blocks, just three blocks to find any row in this 100K row of table. Now, if I just flip this is called a multi-level indexing. If I flip it over, it looks like this. It's like an inverted tree structure. So this multi-level index is also can be organized, and in a data structure world is called an MOA search tree. So let's go to the next slide. So MOA search tree. MOA search means there are M ways, like M children. So in a tree structure, you will have a node, and then there will be children. Depending on how many children you have, you call it two-way search tree, three-way search tree, like that. So in this case, you will always have number of some keys on the node. Keys is number of value pointer pair in one node here. Values and pointer pair, that's very important. Number of children is keys plus one. So in this case, it has only one key and two children. So M is 2. This is a two-way search tree. Two-way search tree is also called a binary search tree. It's not B tree. B tree is balanced tree. Binary tree is different. Binary search tree. The B tree that we see in Oracle, that is balanced tree index. Now, how does it work? So you keep one. Anything less than 15 goes to the left. Anything more than 15 goes to the right. So every node has two children. One goes to the left and goes to the right. This is a two-way search tree, binary search tree. If I have to find 12, you go to 15. 12 is less than 15, so go left. 12 is more than 8, go right, and you find it. And every node has a pointer to the next node. And also, if you are looking for the data, every node has a pointer to the actual data. So that's a little bit different in B tree. I'll show you. Now, in this case, the next image that I have, every node has two keys and three children. So this is a three-way search tree. That means it's anything less than 20 goes to the left, anything more than 50 goes to the right, anything in between goes to the center. If I need to find 12 again, then I go, okay, 12 is less than 20, go to the left. 12 is more than 10 but less than 15, then goes to the center, and then you find it here. Again, every node will have a pointer to the next node and also a pointer to the actual data. The problem with this MOA search tree is there is no rule. As and when the data comes in, the data grows, how you build this tree. Like, should you add in the left or the right? You can add in any way. And there should be an automatic way automated way of managing this index tree, as in when you insert the data or you delete the data. And if you don't have some kind of rules and regulation how you add it, it can be a little unbalanced. Like this left branch can go up to 5 levels, and the right might go up to 2, and the center might go up to 3 levels, like that. It might happen like this. So to and that will be very inefficient in index searching. That will not be good. It will be very costly. So so you need some kind of rules and regulation to make it balance. That's how the balanced B tree indexing has come up. B tree index is a MOA search tree. You can have any number of keys, any number of children, doesn't matter, but it has to be balanced, following some rules. And what are the rules? All leaf node must be at the same level. See, all leaf nodes should be at the same level. This is a two keys and three children, so it is a three-way search tree, but it is a balanced tree index. And some some node may have one, that is at most you can have two keys, and at most you can three children. Some can have one, but the leaf has to be at the same level. You build the index bottom up. You first create the nodes, and then when you get more and more nodes, you split it the node and create parent node. I'll show you exactly how it works. Take some numbers and show you. Now all nodes must have at least m by 2 children before you branch it out, before you split and create another level. So I'll just show you. Let me get some number and I'll show you. So let's take some numbers and try to build a B tree. Here the number of keys is 3, number of children are 4. So each node will have 3 keys and 4 children. So I've built a little bit, but I'll do it again and I'll show you. Okay, so the first number is 10. So I have one node I created, and the next is 20. So each node can have 3 keys, so I can add 20 here. And then is 30, I can still add 30. Next number is, so I've added 10, 20, 30. These three numbers are gone. Next is 40. I cannot have 40 here because I can have only maximum 3 keys in a node. So I need to split it up. So let's split it up. And then, so 40, I cannot have 40. So I'll split up. So I'll bring 30, 40 this side. 30, 40 this side. And I remove 30, 40 from here. And so I have 2 nodes. So I cannot have 2 independent nodes. So I need to have a parent also. So what I'll do is I'll make a parent and move 20 here. So this is how, when I get more data, this is how I split. So you can say all nodes are at the same level, and you can have pointer pointing to the next level, next node. So anything less than 20 goes to the left, anything more than 20 goes to the right. Now let's say we're getting more data. Now 40 is gone, and then you get 25 and 30, 25. 25 is more than 20, so it goes the right side. You put it here. Now next you get 32. 32 is more than 20, but it cannot have 4 keys again, so I'll add it here. So this is how a B tree is created. So 25, 30, 25, 30, 40, and 32, right? So I have a 32. So 25, 32. So I cannot have 32, 40. So at 32 and 40, I move to the right. So I move right, I split this one, 32, 40, and then 32, 40 is gone to the right. This 30 I'll move up. If I'm splitting, I have to move one up to the parent. 32 goes here. Now I need one more pointer to the new node. As you can see, anything less than 20 goes to left, anything more than 32, sorry, not 32, you have to bring 30 up, huh? Anything more than 30 is go to the right, anything in between goes to the center. So I've done 25 and 30, then 16 and 27. 16 is less than 20, you can add it here. Then 27 is between 20 and 30, 27, and then 50. 16, 27 is gone, and then you have 50. 50 is more than 30, so you can add here. So as you can see, and then 46 again, it has to go here, but I have to split it again. So I'll split again and add 40 here, and like that. 40, I'll add 40 here, and then it'll go 46, right? 40 go here, 32 stays here, and then I have to create one more, 46 and 50. 46, 50 goes to the right one. So this way, as and when the data comes in, insert, automatically you manage, you follow this rule, 46 and 50. And then you this one. So anything more than 40, between 30 and 40 goes here, between 20 and 30 goes to the second one, less than 20 goes to the first one, 20 between 20 and 30 goes to second node, and between 30 and 40 goes to the third one, and more than 40 goes to the last one. So this is how you start building up, and when the data is deleted, also the same way you have to remove it. Now let's see this in a one more thing I need to tell you is this is B-tree index, where you have node and there are pointer to the next node. But what about the data, actual data? Where I have a pointer to the actual data? In the leaf node, I have from 10, I have a pointer to the actual data, row ID. That's the row ID here. Here, these are the row ID, actual data here. So in a B tree actually, so what about 20 and 30 in the parent node? There's a leaf node with a pointer. In B tree, what happens is you also have a row ID pointer from here, not only from the leaf node, but also from the branch node, also a root node and branch node, like this. But this is not how Oracle implements it. Oracle implements something called B plus tree. So in B plus tree, the row ID pointer, the pointer to the actual data, row pointer, record pointer, always you have those record pointer, the row ID pointer on the leaf level. You never have this row ID pointer on the branch or root node. That is B plus tree. So in that case, this 20, 20, 30, 40, whatever you see in the root node or branch node, they'll also have an entry in the leaf node. Let's say 2016 and 20. I'll show you in the next slide exactly how it is implemented in Oracle. And then from 20, you will have a row ID pointer to the actual data. This is how it's implemented in Oracle. And I'll tell you the reason also when I'll show the next slide. And this is called B plus tree. So Oracle actually implements a B plus tree, not the B tree, but it's called a B tree index. Let's go to the next slide and see how it is implemented actually in Oracle. So here is one. So I showed you with three-way search key index tree structure with key equal to 2 and 3. But in real world, you can have keys up to 100, 500, even 1,000, doesn't matter. So if you have 1,000 keys, you have 1,000 plus 1 children. So you'll have, as I showed you here, 3 keys and 4 children. So there are 4 children and you point it. Similarly, you can extend up to 100, 500,000. So the more keys you can pack in one block, the more efficient your index will be. And I'll show you how. The larger you can index large tables with a small number of blocks and space. Now let me show you. In this case, it assumes that it can hold 500 entries in a block with 500 keys. The first one is root block. Root block or root node is just one block. It's always one block. Root block. You can see here is one block, and one block it assumes that you can up to 500 rows. As I showed you in the first slide, it can in here in one block it can contain 320 rows. Similarly, depending on how many bytes your primary key is taking and the pointers, it can store up to 400 or 500 depending on that. So here is assumed it can hold 500 rows. Now, so as you can see here, it says key less than equal to 25, there's a pointer, go to left, there's a pointer. Key greater than equal to 50 goes to a pointer. And then there's a leaf. So there's no branch here. There's a root node and then the leaf node. So in one block, it can contain 500 rows. Now, each key points to one leaf block that can again contain 500 rows. That is also a key and row ID. Because it's a leaf node, it has to go to the actual record. So it is a key and row ID. So how many rows you can contain in this leaf block? Because the row IDs are only in the leaf block. So that will be 500. Root node has 500 rows. Each 500 row pointing to another 500 rows. So 500 multiplied 500 is 250,000 rows indexed. So we just, if you have 500 key, if you have a 500 key index structure in just one level, this is one level, because in one level, I'll show you what is one level. In one level, you can index a table with 250,000 records. Now, what is the level? If you go to an Oracle DBA index, there's something called B level, which is branch level. Branch level means it counts only root and branch node, root node and branch node. It doesn't count leaf node. So this is a B level one, root plus leaf node, leaf blocks. So just one B level, you can index 250,000 rows. What if B level 0? B level 0 is just the root node. There is no root itself is leaf. So you have keys and then row ID pointer, no another node pointer. So if you have a small table with less than 500 rows, in this example, you can index it just with the root node, just one block. That's why small tables, it is said that when there is a small table, even if index exists, Oracle goes for a full table scan. So Oracle can, because it has to read one block here and one block, and for the table, it has to read one more block, two blocks. Oracle do, if it's a small table, Oracle read all the blocks in one go using DB multi-block read count. So what is B level 2? B level 2 means root, then one branch level, and then there's a leaf block. How many rows it can index? Again, 500 rows, each row pointing to 500 blocks, 500 rows in the branch node. Again, each row in each block in the branch node can point to 500 rows in the leaf block. So 500 multiplied 500, it is like, it is, I think, 125 million records. 250,000 into 500 multiplied by 500. So it is 125 million. That's only B level to two levels. Now how many blocks you need to read for 125 million? So you read the root node, that is one block. Then you get the pointer, read one more node from the branch node, two blocks. Then get the pointer, go to the leaf block, that is a leaf node, the three block read, and then get the row ID and get the table, read from the table. So four blocks. For 125 million records, you just need to need four blocks. For B level 3, how many rows you can index? This is something called 62.5 billions. So 125 million times 500, 62.5 billion records, and you just need 5 blocks to read, get any data. Root, branch, again one more branch, and then leaf, and then the actual row ID, row. So 5 blocks you need. And why, and the final question is, I'll close with this, why does Oracle keep all the row ID pointer on the leaf? Because Oracle wants to pack as many rows as possible uh, in the in the root and branch node. So you don't have to create a lot of levels, and you don't have to, your navigation will be less. You have to navigate through less number of blocks. Otherwise, if you don't do that, you have to, for every level, root node, branch node, you have to have a key and a pointer and a row ID pointer also. Row ID pointer will take up some space. So instead of 500 rows, entries in one node, one block, you might be able to store 300 entries, 300 keys. Then to cover 250,000 or 125 million, you need more levels. Oracle has to do more navigation and read more blocks. That is very inefficient, will be for larger tables. So to, if you pack more and keys, more entries in one block in the root and branch, so you don't have to create many levels, and then but it still can index large millions and billions of records. But that's the reason Oracle goes for B plus to index and keeps the row ID pointer only for the leaf block. So I think that's all about. Before we go, I'll show you one thing from the database. I'll execute a couple of queries in database and I'll show you how this B level and how these things work. For a small table, I don't have a big table, so I'll have a small table. I'll show you. So let's run. I have one employee table, employees table on HR schema. Let's get the list of indexes. There's a list of indexes. This is employee ID, IDX is valid. B level is 0 because this table has only 100 records, so it makes sense. 100 records, it can just it can index it in just one block. So B level is 0. It has only the root node. And leaf block is 1, which is same as the root node is same as leaf. Average leaf block per key 1. Average data blocks per key 1. If you see B level like more than 3, then you need to take a look at the index. If there is some fragmentation, you need to rebuild the index. You need to take a look at it. Or else for this kind of small tables, Oracle doesn't really go for index. It's directly goes for full table scan because it can read multiple blocks at one time. That's it for today. Thank you.